Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine, just for a second, that you're standing on a beach and you're staring out at this vast, churning ocean.
Okay, I'm picturing it.
Right. But there's a catch. You can't actually see the water, at all.
Oh, wow.
Yeah, the ocean is completely invisible. The only thing you can actually see is the sea foam right on the surface, just floating there in midair.
That is a deeply unsettling mental image.
I know, right? But that's essentially the reality of the universe you're sitting in right now. Everything you can see your hands, the room you're in, the stars in the night sky, that's just the sea foam.
The visible debris.
Exactly. The visible debris. And today, we're going to talk about the invisible ocean, the dark matter, and more importantly, what happens when the most extreme objects in the universe violently collide inside that invisible ocean.
And honestly, the methodology we're looking at today it's just a brilliant shift in how we approach this.
It really is. I mean, we're talking about a completely new way of looking at data we already have.
Right, because for decades, the astrophysics community has been trying to build these massive, ultra-sensitive particle detectors to catch dark matter.
And catching exactly zero particles, right?
Pretty much, yeah. But this new framework developed by this incredible coalition of physicists from MIT, UC Louvain, University of Amsterdam, Queen Mary University, and Oxford, it completely discards the particle detector.
Which is wild.
It is. They are using gravitational waves, the literal ripples in the fabric of space and time, to feel the drag of dark matter.
Which just sounds like pure science fiction.
It does, but it's happening. And the elegance of it lies in the math. It's a highly sophisticated way of predicting how the most extreme gravitational environments in the universe interact with the dark sector.
Okay, so let's unpack this.
Yeah.
Because I want to make sure we're all on the same page before we get to, colliding black holes.
Good idea.
So we have this dark matter. And the accepted number is that it makes up something like 85% of all the matter in the universe, right?
Right, roughly 85%.
Okay, but if I'm playing devil's advocate here, if this stuff is completely invisible, if it totally ignores light, passes right through magnets, passes through the Earth, passes through us, how on earth are physicists so incredibly confident that it's 85% of everything?
Well, what's fascinating here is that the universe gives us a scale that we just can't ignore. We can't see it, but we can definitely feel its weight.
Like a ghost in a haunted house.
Kind of, yeah.
Like you can't see the ghost walking through the wall, but you hear the floorboards creaking under its boots.
That's a really good analogy. The creaking floorboards in this case is gravity.
Right.
Gravity is our only tool to catch it right now. So when astronomers look at, say, distant galaxies, they see the light from those galaxies bending.
Like turning around something in the foreground.
Exactly. Bending around massive invisible structures. We call this gravitational lensing.
Because the gravity is literally acting like a glass lens.
Precisely. General relativity tells us that mass bends space-time. So when light from a distant galaxy travels past a massive object, its path curves.
And we can measure that curve.
We can. And when we calculate the mass required to bend the light that much, and then we add up all the visible stars and gas in that area, the math just doesn't work.
There's not enough visible stuff.
Not even close. There has to be a massive invisible force pulling on that light. And it has to be huge. Hence the 85% figure.
Okay, so we know the ghost is heavy. We know it's there.
Right.
But the astrophysics community has been chasing a very specific kind of ghost for a long time, haven't they? Like the WIMP.
Yes, the weakly interacting massive particle. WIMPs have been the favored candidate for decades.
But this new research, the MIT team, they're pivoting away from WIMPs completely, right?
Yeah.
They're looking at something called a light scalar particle.
They are, yeah. And that pivot is largely driven by, frustration.
Frustration with the empty particle detector.
Exactly. We've built these incredibly sensitive underground vats filled with liquid xenon.
Deep underground to shield them from cosmic rays and stuff.
Right. And we wait for a massive WIMP to just bump into a xenon nucleus and produce a tiny flash of light.
But no flashes.
No flashes. The detectors are remarkably quiet. So theoretical physics has to adapt. We have to explore other candidates that still fit the macroscopic gravity data, the lensing, the galaxy rotation, but maybe behave totally differently on a quantum level.
Enter the light scalar particle.
Enter the light scalar. So in quantum mechanics, particles have this property called spin. It's intrinsic angular momentum.
Right, like an electron has a half spin.
Yes. Photons have a spin of 1, but a scalar particle has a spin of exactly 0.
Okay, meaning it doesn't have a built-in direction.
Exactly. The only fundamental scalar particle we've ever found is the Higgs boson.
Which gives mass to everything.
Right. But the crucial variable here isn't just the 0 spin, it's the prefix light.
Because they are incredibly, almost incomprehensibly light.
We are talking billions of times lighter than a single electron, down to fractions of an electron volt.
Okay, wait. If they are that small, how do they make up 85% of the universe? There must be an unfathomable number of them.
There are, and what's fascinating here is how ultralight masses force us to confront wave-particle duality at an astrophysical scale.
Oh boy, okay. Quantum mechanics on a massive scale.
Right. Because of quantum mechanics, every particle has a wavelength, a de Broglie wavelength.
Sure.
Heavy particles have tiny wavelengths, so they act like little localized billiard balls. But if you take a particle that is absurdly light, like 10 to the minus 10 electron volts, its quantum wavelength stretches out immensely.
How immensely? Like across a room?
We're talking meters, kilometers, maybe even astronomical distances.
Wait, a single particle's quantum field stretches for kilometers?
Exactly. And because these are scalar bosons, they don't obey the Pauli exclusion principle.
Meaning they can share the same space.
Right. You can pack an infinite number of them into the exact same quantum state.
So they just stack on top of each other.
They overlap perfectly. So instead of a bunch of individual discrete particles bouncing around like ping pong balls, they form this macroscopic quantum state. They behave as a single, cohesive, oscillating wave.
Okay, so our ghost isn't a swarm of bugs. It's more like a thick, undulating fog.
That's a great way to look at it, a cohesive classical field.
Yeah.
And that fundamentally changes the game for how we try to detect it.
Right, because a fog isn't going to bump into a single xenon atom in an underground tank and make a flash.
Exactly.
We need something way bigger.
Yeah.
We need to see how that massive fog interacts with the biggest, heaviest things in the universe, which brings us to black holes.
The ultimate gravitational engines.
Right, and the researchers describe this interaction, this fog hitting a rapidly spinning black hole, as something called superradiance.
Yes.
And the analogy they use in the research is it's akin to turning cream into butter, which I love.
It's very evocative.
It is. But here's where it gets really interesting for me. Because, I mean, we usually think of black holes as these ultimate vacuum cleaners, right?
Right, the classic pop science view. Nothing escapes.
Exactly. They just consume everything. So how on earth is a black hole acting like a butter churn? How is it transferring its energy outward to amplify this dark matter fog?
To understand that, we have to look at the geometry of a spinning black hole.
Okay.
It's described mathematically by the Kerr metric. So a spinning black hole doesn't just have an event horizon, the point of no return. It also has this region just outside the horizon called the ergosphere.
The ergosphere.
Sounds intense.
It is intense. Because the black hole is so massive and it's rotating so incredibly fast, it physically drags the fabric of space-time along with it.
Like a spoon stirring thick syrup.
Precisely. That's called frame dragging. And inside the ergosphere, space-time is being dragged around the black hole so violently that it's literally moving faster than the speed of light.
Faster than light, just the space itself, right?
Right, relative to an observer far away. So in that region, it's physically impossible for anything to stand still. Everything has to co-rotate with the black hole. Wow. Okay, so our dark matter wave, this scalar fog, gets drawn into the gravitational well.
Yes.
It enters the ergosphere, and it's forced to spin.
Exactly. But just getting dragged in a circle doesn't mean the wave gains energy.
Right. It's just along for the ride.
For energy to transfer, we need an extraction mechanism, and that happens through a wave scattering process.
Okay, break that down for me.
When the incoming scalar wave scatters off the black hole, a really weird mathematical boundary condition pops up. If the wave is rotating slower than the black hole itself, the wave splits.
It splits.
Yeah, a portion of the wave falls into the event horizon, it's gone.
Okay, standard black hole behavior.
But because of the extreme physics in the ergosphere, that infalling piece of the wave can actually have negative energy.
Wait, hold on. Negative energy.
Relative to the outside universe, yes.
Okay, let me just unpack the conservation of energy here. If the black hole absorbs a wave packet with negative energy, then the black hole's overall mass and its rotational energy have to go down, right?
Yes, the black hole slows down a tiny bit.
So, to balance the cosmic ledger, The piece of the wave that bounces off the part that scatters away has to emerge with more energy than it started with.
The math demands it. The outgoing wave is amplified. It literally steals rotational energy from the black hole.
That is mind-blowing.
It gets better. Here is where the butter churn analogy really shines.
Okay, hit me.
The wave doesn't just scatter once and fly off into deep space. The black hole's gravity creates a potential well. It traps the wave.
Like an orbit.
Kind of like how a proton traps an electron in an atom. So this amplified dark matter wave is stuck. It bounces back and forth in this gravity well, repeatedly passing through the ergosphere.
Oh, I see.
And every single time it passes through, it extracts more energy. It gets amplified again. It's exponential. It is a runaway exponential amplification. The black hole is just dumping its spin energy into the surrounding dark matter, whipping it up, making it incredibly dense.
Turning the cream into butter.
Exactly, until it saturates.
When does it saturate?
Usually when the black hole has spun down so much that it's no longer spinning faster than the wave. At that point, you're left with what physicists call a bosonic cloud.
A bosonic cloud.
Yeah.
So instead of just a diffuse invisible fog, we now have a highly concentrated, super dense halo of dark matter tightly bound to this black hole.
Orders of magnitude denser than the ambient dark matter in the galaxy.
Wow. Okay, so that is the setup. That's the trap we're setting for the ghost.
Right. But there's a problem.
There usually is.
A single black hole just sitting there in space with its dense little dark matter cloud. It doesn't really emit gravitational waves, at least not ones we can easily detect from Earth.
It's too quiet.
It's too quiet. To trigger our detectors, you need a massive perturbation. You need a cataclysm.
You need a binary system.
Yeah.
Two black holes crashing into each other.
Yes.
So this MIT and European team, they set out to build a predictive model to figure out exactly what it looks like when two black holes merge, but one of them or both of them is wrapped in this thick, heavy butter of dark matter.
And that is not a trivial task.
I can imagine. I mean, Einstein's equations are brutal on a good day, right?
Highly complex, nonlinear, coupled partial differential equations. If we connect this to the bigger picture of computational astrophysics, just simulating two black holes colliding in a total vacuum, empty space that took physicists decades to solve.
Wait, really?
Decades. The breakthrough in numerical relativity only happened around 2005.
Just to do it in empty space.
Exactly. So now imagine adding a massive, dynamic, sloshing cloud of scalar particles to that simulation.
The math must be a nightmare.
It introduces immense computational complexity. You have to track the gravity of the black holes, the rippling of the spacetime metric, and the gravitational pull of the dark matter pulling back on the black holes.
Right, because the dark matter has mass, so it's going to exert drag.
We call it dynamical friction.
Dynamical friction. So paint me a picture. How does that drag actually play out as they spiral in towards each other?
So imagine the secondary black hole plunging through the dark matter cloud of the primary black hole. As it moves, its gravity pulls the dark matter particles toward it.
Okay, kind of sweeping them up.
Not quite sweeping them up, but pulling them in so they bunch up behind it. It creates a gravitational wake.
Like a boat moving through water.
Yes. An area of higher density trailing right behind the moving black hole. And because that wake has mass, its gravity pulls backward on the black hole.
Oh, wow. It's literally putting the brakes on.
Exactly. It bleeds away the black hole's orbital energy, and that fundamentally alters the merger.
How so?
Well, in a vacuum, two black holes only lose energy by emitting gravitational waves. They spiral inward at a very predictable, smooth rate. It produces a signal we call a chirp.
The chirp. Because the frequency and the amplitude go up smoothly until they collide.
Right. But when you add dynamical friction from the bosonic cloud, they are losing energy through an extra channel.
Through a drag.
Yes.
Yeah.
So they spiral inward faster than they normally would. The orbital trajectory tightens much faster.
So the phase of the gravitational wave changes. The chirp is accelerated.
The frequency increases more rapidly, yes. And it's even more complicated because the secondary black hole isn't just orbiting the primary black hole anymore. It's orbiting the combined mass of the black hole and the dark matter cloud.
So the team had to use supercomputers to solve all of this.
Yes. They solved the Einstein-Klein-Gordon equations.
Just casually solving the Einstein-Klein-Gordon equations as you do.
Right, which govern the scalar field in curved spacetime. They ran all these simulations to generate theoretical waveforms, a vast library of them.
Basically, they built a dictionary.
A dictionary of what a dark matter merger should look like. They tweaked the masses, the density of the cloud, the mass of the scalar particles.
Okay, so what does this all mean for us on Earth? I mean, they have this theoretical dictionary, but how do you test it?
You turn to the actual data, the public archives of the LIGO Virgo Cagra network.
The LVK network, which, for anyone who doesn't know, is just a global network of massive laser observatories.
The pinnacle of precision measurement.
We're talking lasers bouncing down tunnels that are kilometers long.
Right. They are capable of detecting changes in distance on the order of 10 to the minus 21 meters.
Which is, what is that, a fraction of a proton?
A tiny fraction of a proton.
It's just absurd.
It is. Over their first 3 observing runs, the LVK network detected nearly 100 confirmed gravitational wave events.
Nearly 100 black hole and neutron star collisions.
Yes. But the MIT team didn't just use all of them. They rigorously filtered the dataset. They only selected the 28 clearest, most pristine signals.
The gold standard candidates, why only 28? Why not use all the data?
Because the phase shift, we're looking for this tiny acceleration in the chirp caused by the dark matter drag. It is very subtle.
Right.
If you have a signal that's buried in instrumental noise or, thermal fluctuations in the mirrors, or even a tiny seismic vibration, that noise could easily masquerade as a phase shift.
Ah, okay. You'd get a false positive.
Exactly. By limiting the analysis to the 28 highest signal-to-noise ratio events, they ensured that any anomaly they found was likely astrophysical, not just a bumpy laser.
So how did they actually compare their new dictionary to these 28 signals?
They used a technique called matched filtering.
Matched filtering.
Right. It's standard in this field. You take the incoming noisy data from the detector and you cross-correlate it with your bank of theoretical templates.
You just slide the template over the data until it lines up?
Essentially, yes. If a template matches the signal hidden in the noise, the cross-correlation spikes.
And you have a match.
Right. So they took these 28 pristine events and analyzed them twice. Once using the standard vacuum templates, and once using their brand new dark matter templates.
And they use Bayesian inference to see which one fits better.
Exactly.
Okay, the suspense is killing me. What did they find when they ran the 28 candidates?
Well, for 27 of the 28 candidates, the Bayesian evidence heavily favored the vacuum model.
Okay, so 27 of them were just regular black holes merging in empty space. Or at least the dark matter was too thin to notice.
Right. But one event broke the pattern.
Here we go. GW190728.
Yes. Detected on July 28, 2019, it was a merger of 2 black holes with a combined mass roughly 20 times that of our sun.
Okay, a 20 solar mass collision.
And the Bayesian analysis of this specific signal showed a preference for the dark matter model over the vacuum model.
A preference, meaning it fit the dark matter dictionary better than the empty space dictionary.
Exactly. It exhibited that anomalous phase evolution, that slight acceleration in the chirp that perfectly aligns with the dynamical friction of a bosonic cloud.
Okay, I have to stop you there because I am getting incredibly excited, but I also need to play devil's advocate.
Go for it.
If they found a signal that literally matches the dark matter model, why aren't physicists throwing a global parade right now? Like, why isn't this front page news everywhere? Why is it just a preference?
This raises an important question about the threshold of scientific discovery. And the researchers, particularly Shosu Orikoetsuya from MIT, were very, very cautious about this.
Because in physics, you can't just say, looks pretty good to me.
You really can't. In Bayesian statistics, you calculate something called the Bayes factor. It's a ratio that tells you how much the data shifts your belief from one model to the other.
Okay.
So a Bayes factor might say the data is 10 times or 100 times more probable under the dark matter model.
Which sounds great.
It does. It provides strong evidence, but it does not quantify the probability that the entire signal is just a rare statistical fluke.
Oh, just random noise in the detector that happened to look exactly like the dark matter chirp.
Exactly. In particle physics and astrophysics, the gold standard for a definitive throw-a-parade discovery is the 5 sigma threshold.
5 sigma. I've heard that term. What does that actually mean in plain English?
It means there is a 1 in 3.5 million chance that the anomaly you saw was just random background noise.
Oh, wow. Okay, that is an incredibly high bar.
It is. And the Bayes factor for GW190728 just doesn't reach that level of statistical certainty.
So the signal is strong enough to be in the top 28, but not strong enough to absolutely rule out a fluke.
Right. Or it could be an unmodeled complexity in the vacuum merger itself.
Like what?
Maybe the black holes had incredibly intricate spin dynamics that the standard templates didn't account for. Or maybe their orbit was highly eccentric, slightly oval-shaped, right before they merged.
And that eccentric wobble looked like dark matter drag.
Exactly, or even a subtle calibration error in the interferometer at that exact millisecond. The resolution just isn't quite there yet to eliminate the mundane explanations.
So it's a tantalizing clue, but not the smoking gun.
Exactly. The researchers are demonstrating scientific rigor here. They are not claiming a discovery, they are flagging an anomaly.
They're saying, hey, look at this weird blip.
Right. But more importantly, they are proving that the analytical framework actually works. The pipeline is functional.
If it's there, this is how we find it.
Precisely. GDAL190728 is just the first candidate. It warrants a massive independent review by other teams.
Okay, but even if this specific signal turns out to be a false alarm, say it was just a wobbly vacuum merger, this whole method changes everything, doesn't it?
It represents a massive paradigm shift. Arikoexi actually highlighted a huge vulnerability in how we currently process data. He called it the danger of the wrong dictionary.
The wrong dictionary, I like that. So if we're only armed with vacuum templates, our empty space dictionary, we risk misclassifying the entire universe.
Exactly, because the matched filtering algorithm fundamentally projects the raw data onto whatever templates you give it.
It's an autocorrect.
An autocorrect, yes.
Like imagine I type a perfectly valid but obscure word into my phone. And my spell checker doesn't have it in its dictionary, so it just quietly autocorrects it to something common. And I send the text, without knowing it, change my meaning entirely.
That is a perfect analogy. If your template bank only has empty space black holes, the algorithm will ruthlessly force every incoming wave to fit that scenario.
So if a real dark matter merger hits the Earth, the computer won't crash or say, I don't know, it'll just find the closest empty space match.
It will say, oh, this isn't a 20 solar mass binary in a dark cloud. This is obviously a 22 solar mass binary in empty space, but with slightly weird spin.
It just tweaks the final parameters to hide the anomaly.
Yes. It artificially compensates for the phase shift. It buries the signature of dark matter in the residual noise.
We've basically been reading the universe's text messages, but our autocorrect was hiding the real meaning.
And that is the profound danger. By aggressively matching everything to a simplified vacuum assumption, we blind ourselves to fundamental physics.
We needed a bigger dictionary.
And now we have one. These new dark matter templates give the algorithms the vocabulary they actually need to interpret the data correctly.
That is just brilliant. And, Rodrigo Vicente made a point about this that really stuck with me, a shift in how we fundamentally view the dark sector.
Yes, the transition from the macro to the micro.
Right. Because traditionally, we only look at dark matter on these unfathomably huge scales.
Galaxy clusters weighing millions of billions of solar masses. Measuring the velocity of galaxies spinning inside those clusters.
Weak gravitational lensing stretching across millions of light years.
We are always looking at the universe on the largest possible scales. But this methodology radically alters the focal length.
It zooms way, way in.
It forces us into the extreme microscale of astrophysics. We are moving from the diffuse halos of entire galaxies to examining the immediate environment just a few kilometers outside the event horizon of one specific black hole.
We're looking at the deepest, most extreme gravity wells in the universe.
Testing the quantum mechanical nature of dark matter, its wave-like coherence, its ability to steal energy from spacetime itself.
It really bridges the massive cosmos with particle physics.
It does. And as the LVK network turns back on for its upcoming observing runs, and as next-generation detectors get built.
Like the Cosmic Explorer, right, or the Einstein telescope.
Yes. The sensitivity of these interferometers is going to increase exponentially. The signal-to-noise ratios will climb. We will be detecting thousands of binary mergers.
Reaching all the way back to the dawn of the universe.
Exactly. And for every single one of those events, we now have the mathematical tools to screen them for this invisible drag.
The pipeline is ready.
The theoretical waveforms are there. As Suman Roy emphasized, the volume of data is only going to increase. If light scalar particles really do make up 85% of the matter in the universe, it's mathematically inevitable that we will catch a merger with a signal strong enough to shatter that 5 sigma threshold.
It's just a matter of time.
It is purely a matter of statistical accumulation now.
Man, what a journey. We started with this tiny, invisible anomaly from 2019. We unpacked the wimpy problem, we explored the completely bizarre reality of ultralight scalar fields and macroscopic quantum
We
waves.
talked about churning the dark matter butter.
Yes, the super radiance of spinning black holes, and then the sheer computational triumph of modeling that dynamical friction.
And using Bayesian inference to find that friction hidden in the microscopic ripples of spacetime.
We really are standing on the edge of a totally new era in astronomy. We finally have the dictionary to translate the hidden forces that shape everything.
It's incredibly exciting.
So I want to leave everyone listening with a final, slightly mind-bending thought to chew on.
I like the sound of that.
Think about the broader implications of all this physics we just talked about. If dark matter is this stuff that is completely invisible, that totally ignores light, if it naturally gathers into these hyper-dense quantum clouds around extreme gravity,
Yeah.
how many stars, how many entire galaxies, how much of the actual foundational architecture of our universe has been secretly sculpted by these invisible waves?
A staggering amount.
Right. For all of human history, we have looked up at the sky and observed the universe through light, the electromagnetic spectrum. And we've been mapping the visible matter, which is a mere 15% of reality.
We thought we were watching the main event.
Exactly. We thought the stars were the main event. But if the gravitational waves washing over the Earth tonight are carrying the signature of bosonic clouds and scalar fields, we might have to accept that the visible universe is just the glowing debris.
The foam on the ocean.
The sea foam caught in the currents of a vast invisible ocean. So tonight, when you look up at the night sky, look at the empty spaces between the stars and realize that the void is not empty. We are just finally learning how to feel the ripples in the dark.